for the last session concerning surfactants in solution. So you remember yesterday, I think we stopped here. We were just describing the different phases and the way to recognize phases by electronic or optical microscopy. And we stopped here, and I told you that today we were going to explain, to try to understand a little bit more the change of morphology in the phase diagram. And you remember this sequence of sphere to cylinders to planes. Okay? So, a very easy way to understand this sequence is to attribute to the surfactant a shape, okay, and what is called a shape parameter. This parameter is defined as V, the volume of the molecule, the volume of the molecule. Mainly, this is the representation of the molecule, the geometrical representation of a molecule. So you see that here you have the area, okay. In fact, I draw a volume for the area, but it's the polar head has to be represented only by an area, the occupied area at the interface, okay, or in the micelle. And so this volume, the volume of the molecule, is mainly the volume of the hydrophobic part. Okay, this cone that you see here, this conic volume. Then, in this formula, you have V, and here, the ratio in this ratio, you find A, which is the area of the polar head, and L, which is the length of the chain length, the length of the chain. Sorry. So you see that you make basically what you make. The shape parameter is the ratio between the volume of the hydrophobic part over the area of the polar head. So you compare. Finally, you make a balance between the volume occupied by the hydrophobic part over the area occupied by the polar head. So you compare both, in fact. You make a balance between the hydrophobic part and the hydrophilic head. Okay? And of course, depending on the different surfactants, this shape parameter will vary a lot. Okay? So you can rather define this shape parameter, which is geometric, or what we call, and it's more used than the shape parameter, the spontaneous curvature of the surfactant, which is simply 1 minus this shape parameter. Okay? It's related to the shape parameter, of course. So, when you have a small shape parameter, that means that the volume of you have a small volume of the hydrophobic part and a high area of the polar head. So a big polar head and a small hydrophobic tail. Okay? Just to give you a schematic. So for small values of this shape parameter, C0, the spontaneous curvature, will be positive, of course. And this is typically this representation. This also, a small hydrophobic part and a high area, occupied area by the polar head. And you see that, yeah. Okay. Laser. Okay. Yes, maybe. Thank you. So a small, I said, a big area compared to a small hydrophobic tail. You will find in this case the organization of such a cone. See, if you put several cones like this close to each other, you see that very easily you will form spheres. Okay? Try to imagine that you put another cone close to one. Maybe I can show you this on the next slide and come back after. This is. You see? If you take this cone, which represents the surfactant, and you put another here, and another here, and another here, if you try to fill your space with cones like this, you will form a sphere very easily. Okay? If so this is the case where C0 is positive and high. I come back to the first slide. Then, if you begin to increase the volume occupied by the hydrophobic part, following this representation, this is only a representation, of course, you will increase the volume of the cone, and then you will go to this type of shape, this one. So you enlarge the volume of the cone, okay, like this, keeping the same area. So that means that you increase the shape parameter and then you decrease C0, of course. So C0 is still positive, but it has decreased compared to this situation. And then you see that if you try to fill your space with such molecules, such shapes, it's more difficult to make spheres. Try to imagine that you put this together. You will form cylinders, but less easily form spheres, because the spontaneous curvature has decreased. Okay? If I come back here, so I can even increase a lot the volume of the hydrophobic part and then obtain a kind of cylinder if I go on enlarging the hydrophobic part, okay? And in this case, I will obtain a new, I will put the spontaneous curvature to 0, and then I will form planes. And if I go on doing that, enlarging the hydrophobic part, that means that I go to more hydrophobic surfactants, of course. Then I can, in this situation, completely inverse the spontaneous curvature, get C0 negative spontaneous curvature. For example, this is the case, for example, when you use typically small polar heads with, for example, two hydrophobic tails, which are very large, take a lot of place, and then you enlarge the hydrophobic part, and then you inverse the spontaneous curvature. And when you go from this to this, going through 0, so here you have direct micelles, okay? You form direct micelles, spherical micelles. Here you form inverse micelles, and in between you will find typically the lamellar phase, for example, the planes, okay? So, on the next slide, this is what I resumed here. This axis is the shape parameter. This axis going in the other direction, of course, is C0, the spontaneous curvature. When I resume, when the shape parameter is very small, typically here in this smaller than 1/3, you find direct micelles, okay, with high spontaneous curvature. When you increase a little bit the shape parameter, you decrease, oh, the laser has disappeared. So you decrease a little bit the spontaneous curvature, then you will have cylinders with a smaller spontaneous curvature. And then here you go on increasing the shape parameter, and when the shape parameter is equal to 1, you aim the C0 equal to 0 spontaneous curvature and planes. You see that here typically the shape of your surfactant is a cylinder, and when you try to pack cylinder with each other to fill your space with cylinders, very easily you form planes. Okay, and then I could have gone more in this direction. Then you will find all this structure but inversed. Okay, the inverse structure in theory. So, you have to be aware that, of course, this shape parameter is related to the chemical structure of the surfactant. For example, SDS is typically a surfactant of high C0, of high spontaneous curvature, so it will easily form spheres, okay? And to the contrary, AOT, I don't know if you remember this in the first lecture, I described a very hydrophobic surfactant with two hydrophobic tails which were enormous and taking a lot of place, and I told you this is typically, this surfactant is used to make inverse structures, inverse micelles. So AOT is typically a surfactant which will follow this kind of shape. This is right. I gave this example here, an hydrophobic surfactant. So you will form directly. It will be very difficult to form direct micelles with AOT. Generally, it doesn't form direct micelles, okay? But, okay, it's related to the nature of the surfactant, but it's also related to the environment of the surfactant. Once again, to the physical and chemical parameters that you will have around. The example is given here. SDS is in pure water has this type of shape parameter, so a high spontaneous curvature. But if you put SDS into salted water, then you decrease the spontaneous curvature. Why? Because remember, when you have salt, the polar head can be closer to each other than you don't have salt, because there are less electrostatic repulsions. And that means that the area that occupy the polar head is smaller when you have salt than when you don't have salt. So that means that you increase the shape parameter of SDS when you put salt in the solution. Okay? So you see that only by adding something in the solution, salt, but it will also be the case for some other surfactant if you increase the temperature, if you add a co-surfactant, we will see this later, then you change the shape parameter and the spontaneous curvature. And this is the reason why in phase diagram you can go from direct micelles to inverse micelles, because you change the shape parameter playing with the physical and chemical parameters like temperature, salt, and so on. Okay? Okay. Next slide. So of course, this is a kind of empirical description, this shape parameter, okay? This spontaneous curvature. But of course, it is related to thermodynamics arguments, and I will try to explain you this now. So what are the thermodynamic arguments behind this approach? The idea is that behind this spontaneous curvature, you have the notion of energy, always and always. It's always a question of energy, okay? And the energy is monitoring the transition in the phase diagram. I only give you an example. I could have done such slides for any change, any transition in the phase diagram, but I think it's enough to understand the arguments to give one example. The example, the transition from spheres to cylinders. The question is, why do we have this type of transition? Why do we change from spheres to cylinders in the phase diagram? So we have to understand that there is a competition, as always, between energy and entropy. And here, if you consider a micelle like this one, an elongated micelle like this one, the energy comes from the curvature of the system, because you have bending curvature, so you have a curvature energy. So imagine a sphere first. So not this example. If you imagine a sphere, in a sphere you have a lot of curvature, of course, because you have curvature in every direction of the sphere, if you consider it. And it's very curved, okay? You have a lot of curvature. So a lot of energy of curvature. You have to put energy in the system to curve the plane of surfactant, if you want, and to make a sphere, okay? In a cylinder like this one, you have high curvature energy here on the top, okay? Not on the top, on this part of the cylinders. But here, in this part, you have less energy because you have curvature in one direction, but not in the other direction compared to a sphere, okay? So it costs less energy to make a cylinder than to make a sphere. This is, except that here you have two hemispheres to end the cylinders. The two caps of the cylinder have a lot of energy of curvature. So what are the consequences of this approach? If you follow the curvature energy arguments, you have to decrease as much as possible the curvature energy in the system, because it cuts energy. So if you have two small cylinders like this one, it's more favorable to form a big cylinder. Sorry for the drawing, which is very awful, but it's a cylinder, okay? So it's easier, it's more favorable from an energetical point of view to put to make a big cylinder than this one than to keep too small. Why? Do you know why? How many caps do you have in this situation? 4, okay? And in this situation, if you make a fusion between the two small cylinders, you obtain a big one with only 2 caps. And because the caps are the most costly part of the cylinder, it's more favorable to do this. Okay? So, yeah. So, of course, if we follow only this argument, the system will make a giant, an infinite cylinder, of course. If you have small spheres, then you begin to put 2 spheres together, you make a small cylinder. Then you have a lot of small cylinders, you make bigger cylinders, and so on. And if you only follow this curvature and energy argument, you make an infinite cylinders. This is not what we see in the phase diagram. We don't have phases made with one unique infinite cylinder. So this is because you have a balance, of course, of that. And the balances are the entropic arguments. The entropic arguments promote an increasing number of objects. You know that entropy is always as big as possible, and it's proportional to the number of objects that you have in the solution. So it's from the entropic point of view, it's better to have as most as possible objects in the solution. So from the entropic point of view, you will keep spheres. The smallest object, sphere, a lot of spheres. So you have a balance in between these 2 arguments. So finally, this results in a compromise between the two, between the 2 arguments. And typically, you will have spheres for, I've written chi smaller than a critical chi. Chi can be anything in the diagram. Concentration, temperature, any once again, thermodynamical parameters. But you will have a chi C, a critical thermodynamical parameter, below which you have spheres, but above which it's too costly to keep spheres, and then you will have cylinders, but not infinite cylinders, a finite number of cylinders. Okay. Yeah, maybe we use the microphone if you have a question.
In the before slide, you have show that you have cylinders or have isotropic spheres, I don't know, or have slides
Or
layers. Well, my question is, would you have isotropic mixed with cylinders or layers, and between the layers maybe micelles or?
Yeah. This is a good question. If you remember in the phase diagram, I've shown you what I call binodals, I don't know exactly in English, but these lines where when you are at this concentration, at a concentration where you are on this kind of segment of line, the system is diphasic. So of course, for some concentration, the equilibrium state will be a phase separation between spheres, for example, and cylinders. Okay? Here I just explain basically the arguments that led to a transition from sphere to cylinders. But of course, because these transitions are first order transition, you will always find diphasic systems in which the energy will be minimal. You will have a minimal energy when you will be at the phase separation. You will have an equilibrium between spheres, for example, and cylinders. I don't know if I answered your question. And it's the same between, for example, cylinder and lamella. You will also find a phase transition, so a situation in which you will have both a phase separation in between. But then, if you go on increasing your chi, okay, then you will completely be in lamella, or when it decreases, you will completely be in a cylinder. Okay, this is related to the nature of this transition. They are first order, so you have phase separation. Okay. So is it clear how we? So any phase transition in the phase diagram can be explained by this type of argument. This balance between enthalpy and entropy. Okay. If you have, for those who have followed the polymer lecture, it's the same. You always have this, with Olivier, this balance between enthalpy and entropy. And then the equilibrium is when you add the entropy part and the enthalpic part, you have to minimize, finally you minimize the Gibbs energy, and this Gibbs energy gives you the equilibrium state, okay? So if we go back to the diagram, just to remind you that we find this type of transition. For example, here, chi, if I follow this vertical line, chi is T. Remember, it's a non-ionic phase diagram, okay? Is the temperature. And indeed, in this diagram, we can go directly from, for example, spheres to lamella. This is because in this situation, if you calculate the Gibbs energy, it's not favorable to go through cylinders, okay? But you will directly go to lamella. You will have a strong decrease of the C0. But I didn't say anything about this before. We even find within the isotropic domain the formation of cylindrical micelles. You remember the TEM images that I've shown yesterday? I've shown you a coexistence between spheres and some kind of spaghettis, if you remember, micelles, which were very long, typically cylindrical micelles. So you find even in this domain a kind of transition between spheres and cylinders. So we find this in the diagram, of course. So if we go back to the diagram, let's make a comparison between the non-ionic and ionic. So the energy is changing, okay, because, of course, entropy is changing, but also enthalpy is changing, and enthalpy is changing because curvature is changing. And curvature is changing because the spontaneous curvature C0 of surfactant is changing. And the question is now, what makes the change, what makes C0, the energy, vary in each case? It's not the same argument, of course. In the case of the non-ionic diagram, phase diagram, it's probably different than in the case of the ionic surfactant, okay? So what makes the change of curvature in the case of the non-ionic surfactant in the dilute part? So here I plotted an axis representing T, which is the chi parameter in the case of the non-ionic. And the situation is the following. When you are at low temperature, once again, this is the story of good and bad solvent of polymers, of polar polymers. I represented here my surfactant. You see here a kind of chain, blue chain, which is the hydrophilic head. And then here you have the black chain, black tail, black hydrophobic tail. When you are at low temperature, these small things here represent the water molecules. Okay? So when you are at low temperature, the hydrophilic head is very well hydrated by the water molecules. So you have a lot of water molecules inside, around the OH groups of the hydrophilic head. So your hydrophilic head is swollen. It is swollen by water. So the area occupied by the hydrophilic head is large because it's swollen, okay, by the water, well hydrated. We say that the surfactant is in good solvent. So if the area is large, the shape parameter of the surfactant is high, so the spontaneous curvature is small, excuse me, and the spontaneous curvature is high. Sorry, the spontaneous curvature is positive and high. And you have this kind of shape, and you form typically spherical micelles. So, thank you. Then, if you increase the temperature, you dehydrate typically the polar head. So you have a kind of constriction. You observe a kind of constriction of the polar head because you don't have anymore the water molecule inside the hydrating the polar head. So it shrinks. Okay. The occupied area is smaller. that means that you change your shape parameter, and then you go to much smaller spontaneous curvature. You can even aim. You can even have zero spontaneous curvature, and then you will form lamellar phase. And this is what we observe in the diagram. So the effect of temperature is easy to understand by this mean. In the case of the ionic surfactant now, it's different, because remember, in the case of the ionic surfactant, the chi parameter is no more the temperature, but the addition of a co-surfactant. And what happens when we add this co-surfactant to micelles, to existing micelles? You remember that the co-surfactant doesn't form any micelles alone. It will participate to the formation of surfactant micelle, existing surfactant micelles, but it doesn't form alone micelles by itself. But we can attribute a shape parameter to the octanol molecule. And typically, the shape parameter is this one, a small OH head with an alkyl chain, so typically a cylinder. Okay? This is reasonable to attribute this shape parameter. So, if you imagine that you don't have any octanol in the phase diagram, you have SDS surfactant. We know that the shape parameter is this one, so the curvature is high. It will form, of course, spherical micelles. And then you begin to add a little bit, or even more and more, octanol molecules. They will go in between, typically in between the SDS molecules. And of course, because their shape parameter is different, the curvature is smaller, you will go from this high spontaneous curvature to this low spontaneous curvature, and you will form plans layers, of course. So this is a bit schematic, of course, because here it doesn't mean that you don't have any octanol. There is no place in the diagram where you have no octanol molecules, but this was only to explain to you, if you have a few quantity of octanol, you will keep the spherical shape, but if you increase a lot the octanol quantity, then you will force the curvature to change and to go to the planes. So you see, completely different arguments, but same effect at the end, same final result. So to resume, in this dilute regime, I insist, we are in the dilute regime, okay? So in this part of the diagram, typically, the hexagonal phase, I remind you, is no more a dilute phase. Is no more a dilute phase. So typically, in the you will be in the dilute regime in the isotropic phase. Okay?
You are very far from the CMC.
Repeat your question for the.
You are far of from CMC.
Yes, you are far from CMC, because remember, CMC is typically 10 to minus 3 mol per liter, and you are well above the CMC. You are so well above the CMC that in this linear representation you don't see the CMC line, because it's too close to the vertical axis, to the y-axis. Okay, we are far from CMC, of course, but well, in fact you're right. Here you are far from CMC, but at the beginning of the isotropic domain, you are very close to the CMC. The isotropic domain is very large. It goes from the CMC line to the hexagonal phase. So this isotropic domain goes from very diluted regime to concentrated regime. You keep your isotropic regime in a very large range of concentration. So to resume, we have seen that the shape of the micellar aggregates is related to the spontaneous curvature of the surfactant. It's a very easy, convenient way to explain how it works, this spontaneous curvature. We have, this induces a standard sequence from spheres to cylinders of finite size to infinite layers. We have seen that. The vertical axis, when you move along the vertical axis, you have a decrease of the spontaneous curvature, and we have seen that there is a new universality of all the diagrams, whatever the chi parameter. Okay, always the same kind of situation, same influence of curvature. So this is for a dilute regime, easy to understand. Now, what happens when we go to more concentrated regime? I will not spend a lot of time describing this. I will only give you the main contents, the main arguments which are behind this approach. But this is the next step, the effect of concentration, because when you go to a concentrated regime, you have interactions appearing between the micelles, and this, of course, has to be taken into account in the Gibbs energy, in the final energy of the system, Gibbs or free energy. So, let's go to surfactants in concentrated regime now. In fact, we have to construct, you understand that now, we have to construct the energy of the system. This can be the free energy of the Gibbs energy, whatever. I mean, you have to measure to construct the energy of the system. So you have to know the ingredients of this energy. In the diluted regime, you only have entropy and energy of curvature. Okay? In the concentrated regime, you will also have energy of curvature because you also have micelles which are curved. Okay, you will have entropy, of course, always, and you will have to add to this interaction potential, energy of interaction between the micelles which are now very close to each other. So, very quickly, what do we find what are the ingredients of the interaction potential between when you have two micelles, for example, two cylindrical micelles like this one, but could be the same with spherical or planes, close to each other. So if they are separated by a d distance, you probably know that you have first an attractive interaction, which is called the van der Waals potential. And this van der Waals potential varies very strongly with the distance. And you have here, if you approach too much, of course, two objects, whatever the objects, molecules, hard spheres, and also cylinders of surfactants, when they are too much approach, here you have infinite repulsive interaction. That means that you cannot fuse them, okay? And when they are too far from each other, in this part of the interaction potential, the potential tends to zero. That means that you have no more interaction. This is a dilute regime, for example. And in between, there is, in general, a range of distance between which you have an attractive interaction. This is why you form molecules with two atoms. I mean, this is a universal potential. Okay. So the same for micelles. And then this is basically the only attractive interaction that you will have. The other interactions are repulsive between two walls of surfactant. Okay. You have typically two kinds of repulsive interactions. They can be short range, like steric hindrance, steric interaction. You have here the potential varying exponentially with the distance between the two walls of surfactants. And it's typically short range because this characteristic length is in between 3-4 angstrom. This is the range of the steric interaction. It's very short. To the contrary, the electrostatic repulsive interaction, I already talked about them before, are long range because they are characterized by what we call the Debye length, and this Debye length is varying typically from a few nanometers to a few tenths of nanometers. It's much larger than the critical length of the steric repulsion. And for example, this is this Debye length that is varying when you add salt in the solution. You can tune it by changing the ionic strength of the solution, the salinity. So of course, you have to put this potential, this interaction potential, in your free energy or in your Gibbs energy when you calculate the energy of your micellar phases. Okay. Second ingredient, we already talked about this, the curvature. So until now I didn't explain you how this energy is calculated. I don't want to explain exactly how it's calculated because it's not so easy. It's typically usual thin elastic sheets theory that you can find in Landau leaf sheets, for example, if you have already opened this kind of books. So a lot of calculation, but simply just to explain you the content of this energy, the full content of this energy, you have two terms. This first term is an integral over the surface of the micelle that you have, cylindrical, plane, or spherical. So you integrate this term over all the surface of the micelle. And what do you find in this term? You find different things. You find again the spontaneous curvature of the surfactant that we described before. So you see that it's very important. You find it in the calculation of the energy, of course. But you also have two geometric curvatures, C1 and C2. If you consider this a sphere, or for example this a shape, you in the case of sphere, of course, C1 is equal to C2. You have the same radius of curvature in two directions. But as soon as you change the shape of the micelle, then you have two curvature to take into account. So this is the curvature of the shape of the micelle itself, and this is the spontaneous curvature of the surfactant at the scale of the surfactant. It's a little bit different, okay? But the three are integrated in the energy, and you also have two elastic constant, kappa and kappa dot, yes. Kappa and kappa dot, and these are elastic constants. They are completely dependent on the type of material. You see, for example, a sheet of paper or a sheet of steel or of carbon, of graphene, for example, they don't have the same, of course, elastic constant. And it's the same when you change your surfactant, you don't have exactly the same value of elastic constant. But when you integrate all of this, you can calculate the energy. This is another term which is called the Gaussian part of the energy. In fact, it's something which can be easily calculated and which is constant. It takes into account the defects of the surface. For example, if you go from a lamellar phase to a sponge phase, you create a lot of defects inside, and these defects will be taken into account in this part of the energy. Well, whatever the difficulty of calculating this energy, it's possible to do it, to compute this, to calculate it. And I just don't want to go into details, but just to give you a few examples, when you calculate this curvature energy in different cases, layers, cylinders, spheres, cubic phases, for example, you will find different type of calculations, and it also depends if you have a monolayer or a bilayer of surfactants. It changes also your calculation of curvature energy. No, it's not useful to describe all of this. Just we can see that in some cases there is no dependency of the curvature energy on the size of the micelle, on the size of the micelle. For me, micelle, it can be a lamella or a sphere or a cylinder. It doesn't depend on the size. In the case of a plane interface, so bilayers, so lamellar phase, you even don't have any curvature energy. There is no curvature energy in a lamellar phase. Okay. There is curvature energy in the case of cylindrical, okay, with depending on air, which is the radius of the cylinders, of course. In the case of spheres, bilayer of spheres, for example, typically, what is a bilayer of sphere? Vesicle, for example. Vesicle can be considered as bilayers making a sphere. It doesn't depend on the size no more. And it doesn't depend no more on the size when you have a bilayer of cubic bilayer, but it depends on the size when you have a monolayer, a cubic monolayer phase. Okay, so you see that it's very varying depending on the fact that it's a bilayer or a monolayer and on the morphology. It can be calculated, and it can be integrated in the final calculation of the energy of the system. So it's a bit formal, but sorry, but I think it's useful to understand how we construct this energy. In this case, it's the free energy, F. You have, so, the energy of curvature. You have the interaction potential that we described before. So, for example, if you are in the case of a ionic surfactant, you will put electrostatic repulsion, and you will only put steric repulsion in the case of a non-ionic surfactant. You have to adapt to fit to the situation, of course. And then, last but not least, you put entropy. You calculate, you add all these terms, and you calculate your free energy. You calculate each for each phase, and of course it will be different in the case of a sphere, cylinders, or lamella, because the C0 is different. The C0, the C1, and the C2 are different, so you will have change in this energy. You can compare the free energy of each phase and try to see in which situation you will have the equilibrium state. That means you will try to find the lowest free energy as possible. So technically, but we plot the free energy versus the concentration of the volumic fraction of surfactants, and we plot the free energy. For example, the curve for micelles, the curve for spherical micelles, the curve related to hexagonal phase to lamella, and then we compare this curve and we try using the double tangent method to find the situation of equilibrium. And sometimes we find two phases. I don't want to go into more details, because if you want to go into more details, you have to make exercises around this, and it's not the purpose of this lecture. It's just to give you an idea how we manage to understand the different phase transition and the different change of morphology in these phase diagrams. Is it clear? Okay. Okay. I end with the phase diagram, and after I will only go to give you some example of how we use surfactants to make materials. Okay, so I like to end with phase diagram, just showing you another representation, which is widely used also by people working with the phase diagram. If you are using surfactants, you have to be able to use the bidimensional representation that we have seen before, but also the ternary representation, because, for example, in the case of the SDS octanol water diagrams that we have studied before, I've shown you a binary representation, but I've done, to be able to make this binary representation, the y-axis was represented the ratio between octanol and SDS. And it's a way to go from a ternary representation to a binary representation. Because in your system, in fact, actually, you have three components: water, SDS, and the co-surfactant. And sometimes it can be more useful, more convenient to use the ternary representation instead of the binary representation. I just want to show you that we find exactly the same information in both representations, of course. So this ternary representation, it's not the same phase diagram that I've shown before. In this case, it's SDS, water, and decanol. It's just a chain of the co-surfactant. It's a bit longer. It's 10 carbon in the chain instead of 8 carbon in the chain. So you see this representation. Each top of the triangle. Corner. Thank you. Each corner of the triangle represent one of the three components. Okay, and here you can read the composition of here SDS on this axis. On this axis, decanol. Okay, and on this axis, water. First of all, you see that the axis doesn't go from 0 to 100%. It represents massive fractions. Okay, so here it's massive fractions. It doesn't go from 0 to 100% because it's a zoom in the ternary diagram. Okay, it's a zoom where you have interesting phases. Okay, to see. So it's a zoom, but in this zoom, you have separation lines like this one. In between gray zones, in fact, these gray zones are diphasic. Okay, we could have plotted the binodals instead of plotting this small dots here. It would have been better to put the binodal, but well, it's extracted from literature, and I took it like it is. So the gray parts are the diphasics, the phase separations. And of course, the other parts with letters represent the monophasic domains, and we find the same monophasic domain as before. We have to find the isotropic, the cylinder, and the lamella, and maybe some other more exotic phases, but we have to find this. So the isotropic domain is here, indeed. It's called L1 here instead of I. This E phase is the hexagonal phase. Sometimes the way hexagonal lamellar phase are called are varying from a publication to another. There are different letters which are used. Instead of H alpha, it's E here, hexagonal. And here the D, this D phase is the lamellar phase, okay? So imagine that you prepare a sample, an isotropic sample here at this concentration. In M point if you want, but imagine it here. And imagine that you move, or here. You move in the diagram like this. You add decanol to your system, basically, because here you have the corner, the decanol corner. You will go, here you will cross through the transition, and then the hexagonal, and then, if you go on, the lamella. So you see that you find again the famous sequences, spheres, cylinders, lamella. You will never have the lamellar phase here and the hexagonal phase here. It's not possible. And whatever you change, whatever the way you move, going from the isotropic phase, you will always go through cylinders before going to lamella. These two more exotic phases, NC in ND and ND, I presented them last time, during the last lecture. These are nematic phases. Calamitic, which are kind of cylinders too, and discotic phases, okay? Finally, discs and lamella are not so far. You have, in a disc, you have two planes, okay? And a ring around the disc, of course, but it's not so far from a lamellar phase, a phase disc, if you imagine it, okay? So when you go from this phase to this one, it's a little bit as if you change your curvature, you diminished your curvature, okay? So you are always in the right direction, I mean, diminishing your curvature when you go in this direction, okay? Do you know how to read the composition of a sample in such a diagram? Have you ever worked in a diagram like this one before? No? Yes, maybe some of you? I've written an example here. Suppose that you prepare a sample in the isotropic domain. This sample, this M point. How do you read the composition of M? It's very easy. I've written here the composition. This is the SDS corner. So to read the composition in SDS, you will read it on this axis. What do? You take a parallel to the main triangle axis, which is in front of the corner of SDS, and then this parallel, you cross this parallel with the SDS axis, and then here at this point you read the concentration of the massive fraction in SDS, 23%, okay? And the same for the other. Decanol, you read the decanol on this axis, okay? Because you have this arrow here towards decanol on this axis. So you take the parallel of the decanol corner. This is the parallel. You take a parallel to the main axis, which is in front of the decanol corner, and then you cross this parallel with the decanol axis. You have 2% of decanol, and the same for water. And of course, the sum should be 100%, of course, because there are massive fractions. Okay? This is the way you read it. Okay. So with this, I have finished with the phase diagram and the main concepts around surfactants. So after that, I will go to more application example using surfactant. It's not so long. And if you have maybe questions about the phase diagram at this point, I can try to answer to it. So Camilo, you wanted to ask a question?
You can build this kind of this is empirical phase diagram, I think.
This is
Empirical, experimental.
no, it's experimental. Yes,
Uh,
absolutely, it's experimental.
But we can imagine to calculate from simulation according with the surfactant characteristic. We can build the same phase diagram.
Yes, absolutely. This is an experimental phase diagram. That means that people who I should have written the reference of it. I did it for the previous one, but I forgot. But this is experimental. That means that the people who have done this phase diagram, I don't know if you can imagine the work it is. Because, yes, how many points? Because when you don't know anything about a phase diagram, you have no other choice than making a lot of samples and trying to find the separation lines. Okay? So as soon as you see two phases, you know that you are at the border of a monophasic domain. Then, how do? You examine your tube using the methods I described before, microscopy, birefringence, and so on. You identify your phases and say, yes, in my diphasic tube, I have a lamellar phase with, I don't know, with a calamitic nematic phase. So I know that here I am at the border between a nematic and a lamellar phase. So I begin to know where is my lamellar phase. But you have to do this. You see that you have to do this for all this diagram. It's a 2D system, a 2D diagram that you have to plot. So it's a lot. It's a very enormous, huge work. And all these works have been done typically in between the 80s and the 90s years. It was widely done in many labs. There was a lot of work around surfactants. And now, of course, people, it's no more time, I would say, to make huge phase diagrams than this one, but it's very useful to know this phase diagram because now in labs, people are using phase diagram, are using the organization, the particular organization of surfactants to make materials. I will show you examples after that. For example, to template matter, okay? So all this work, this huge work which has been done in the 80s around phase diagram is now useful for people to make new functional materials, for example. So it's very useful. Okay? But yes, I didn't answer to your question. Finally, sorry. You told me, is it? Yes, exactly. Absolutely. If we calculate using, it's absolutely possible to obtain such a phase diagram by calculation, of course, using the models, the Gibbs energy, the way using the appropriate calculation of Gibbs energy. So putting the right C0, the right C1 and C2, and then calculating the Gibbs energy, it's possible to find. So a lot of people have also worked on simulations, calculations, to simulate the borders of these phase diagrams. So, and it works very well because now it's well understood, people know how it works, and it works. Okay. I don't know if in Kumana or in Merida you have questions about the phase diagram. Maybe it's time. You hear me? No? You don't have any question? Maybe at the end of the talk, if you want. Okay, some application examples of surfactants, because what I've described before, it's rather theoretical, even if you have a lot of experimental work behind this. But now, why surfactants are useful in what situation? There are many examples of application of surfactants. They are all around, I would say, in industry, but also in research. Sorry. I have chosen, it's not exhaustive, I have chosen a few examples. And I just want to begin with emulsions. You probably know emulsions, and I don't want to spend too much time on this because you can make a complete lectures around emulsions and around the behavior of emulsions. But I just want to give you a few notions around emulsion. What are emulsions? An emulsion is a dispersion of two non-miscible fluids. Typically, the main example is oil and water, for example. So you know that when you mix oil and water, if you do this in your kitchen, if you try to mix oil and water very, very quickly, in a few seconds, you will obtain, I need my pointer, sorry, this situation, a phase separation between oil and water. Why do you obtain this? Because it is the equilibrium state. It is the minimum of energy. If you calculate the energy of the system, you will have the minimum of energy here. Well, so it's possible to mix oil and water, of course, yes, very temporarily. I mean, during a few seconds, if you shake it very strongly, you can make droplets of oil into water or droplets of water into oil. You will be in this situation, but because the energy is very high, you have to shake a lot. You have to put energy in the system to obtain this. But this is an unstable state, and very quickly the system will go back to this situation. Surfactants are very useful because they, thanks to surfactant, it's possible not to obtain a stable state, but to obtain what we call a metastable state, which is this intermediate state here. Of course, it's a much higher energical state than this one, which is the lowest energy state, the most stable one, but the energy of this system here is lower than this one. So, at least from the kinetical point of view, it's possible to stabilize, we say metastabilize this system. Why? Because if you make a zoom of this, here I plotted droplets of oil into a continuous phase of water. If you make a zoom on these droplets, what you will see, you have droplets of oils, and at the interface between oils and water, there is surfactant. So we added surfactant to the system, and when we add surfactant to the system, the surfactant goes to the interface. You know why? Of course, because it's amphiphilic. And the main consequence of this fact is that you decrease the surface energy between the oil and water. In this system, what costs a lot, it's the quantity of interface and the energy of interface that you have. Remember, I talked about surface tension at the beginning of my lecture. Here, in this system, the surface tension is enormous. You have a lot of interface energy. And remember, one of the main effects of a surfactant is to decrease the surface tension of water, of the interface made of water. So here you have a water-oil interface, and the surfactant will decrease the surface tension between oil and water. And if you, so the surface tension, remember, it's the energy divided by the surface. So if you multiply the surface tension by all the surface that you have here, the total energy that you find is less than in this case, thanks to the surfactant. So this is the reason why it's possible to stabilize, partially, to stabilize this system. So with the surfactant, you will reduce the energy, and you will also increase the kinetics of the system to go back to the equilibrium state, the phase separation. So you have to be aware that emulsions are metastable state. The stable situation is always the phase separation. So any emulsion that you prepare, that you formulate, will go back to the phase separation. But if you play well, if you play very well with the surfactant, you will have a very long kinetics to go back to this equilibrium state. And some emulsions are stable during a few seconds, some other during few hours, and some other are stable during several years. Okay? You have many examples of emulsions, very current example of emulsion. Do you have ideas of emulsions? You have already eaten mayonnaise? You like this? Okay. So mayonnaise is typically an example of emulsion. What is the stability of a mayonnaise? Of course, you keep it in the fridge, but it's mainly to avoid the development of bacteria inside. But typically, it can be stable during several months, before. But if you forget your mayonnaise tube a bottle inside your fridge, if you forget it too long, you will observe at the end a phase separation. You will have oil and grease, oil from a side, and water on the other side. It's not, you don't want to eat it when you see that, okay? So it's very important. The formulation and the choice of the surfactant is very important. There are plenty other examples. For example, paints. The paints are emulsions. Of course, in cosmetics are full of emulsions, creams, shampoo, and so on. And of course, the stability of this, the metastability, the kinetics of this stabilization is very important. You have to be to monitor this, and it's the choice not only, but the main point is the choice of the surfactant. Okay. So if you choose your surfactant very well, you control the stabilization of this emulsion, but also the emulsion curvature. You can have actually you can have two situations. The first situation is droplets of oil into water, but you also, this is what we call a direct emulsion, but you can also have droplets of water into a continuous phase of oil. And mayonnaise it's typically this case. Mayonnaise, it's droplet of aqueous, not exactly water, but something which is aqueous, into oil. The continuous phase is oil. You put a lot of oil when you make mayonnaise. If you make it by yourself, you put a lot of oil. It's not very good for health, but it's very good for taste. So you are in this inverse. This is what we call an inverse emulsion. This one. So how do you go from a direct to an inverse emulsion? By monitoring. It's monitored by the surfactant, and once again by the spontaneous curvature of the surfactant. If you have a positive C0, you will have direct emulsion. If you use a surfactant of negative C0, you will have an inverse emulsion. Normally, it should be blue inside here, because it's water. I put water in blue and oil in yellow. Okay? So you see that it's very important to know your surfactant very well, and in formulation, in industrial formulation, of course, the choice of surfactant, and of course of the other ingredients, because you have a lot of other ingredients also, are very important. Second example, microemulsions. So this is a little bit, how to say this, it can induce mistakes, this name, because you can think that microemulsions are very small emulsions, but it's not the case, because microemulsions are thermodynamic, are systems which are at the thermodynamic equilibrium state. So it's not an emulsion. It's not the same thing. I don't know why it has been called microemulsion, because it looks like emulsions, of course, like small emulsions, but be careful, it's not the same type of systems. What are microemulsions? Well, it's also a system where you put water and oil. It's a mixture at the equilibrium state. It's different from emulsions. You also use surfactants inside, and very often you have a mixture of surfactant and co-surfactant to make these microemulsions. It's at the equilibrium state. What it is swollen micelles, swollen with oil. So now, instead of having only the hydrophobic part together without anything, you will have oil at this place. So you can swell the micelles with a certain amount of oil. Okay? And the characteristic size of this swollen micelle is very small. It's a little bit more than the classical micelles that we have described in this lecture, but it's not more than 10 nanometers. It's very small. Generally, emulsions are bigger. This is probably the reason why it has been named like this. But this is at the equilibrium state. That means that if you put the surfactant, the water, the oil, generally a co-surfactant, all together, even if you don't mix, you let it on your table, you come back a few hours later, you will have an homogeneous system, homogeneous or not, we will see this after, but you will have the system at the equilibrium state. The different moieties, water, oil, surfactant, will diffuse inside, and you will go alone to the equilibrium state. Whereas for emulsions, we have to put energy in the system to shake it, or to use temperature to mix it. It's not spontaneous in the case of emulsion because it's not the equilibrium state. So it's at the equilibrium state. And then all we have said before concerning the phase diagram are you have the same arguments to describe the phase diagrams that you can obtain with microemulsion because the systems are equilibrated at the equilibrium state. So depending on the curvature, spontaneous curvature of the surfactant, you will have direct micelles with oil inside, water outside. Inverse micelle if you go to negative spontaneous curvature with oil outside, water inside. Or also lamellar structure with a spontaneous curvature which is equal to 0, lamellar structure, but this time instead of having only water in between the polar heads and nothing here, only the hydrophobic tails, in between the hydrophobic tails you can put oil. So you will have a sandwich between water, oil, water, oil, water, oil. And you can then encapsulate, you can, yes, you can take oil in your system. Have you, if I take the example of mayonnaise that I described before, you know that a mayonnaise is not transparent, of course. Emulsions are not transparent, okay? Micro emulsions are completely transparent. Even if you have 15%, 50% of oil, 50% of water inside, they are completely transparent because you have swollen micelles which are very small and they don't scatter light, like in the case of emulsion, okay?
You have an example of microemulsion?
Take the microphone.
Do you have an example of one microemulsion in your mind? You can.
Yes. An example, you mean using, yeah. Well, if you mixed SDS, for example, once again, SDS, pentanol, so a very short co-surfactant, pentanol, dodecan, which is the oil, an alcan, so the oil, and salted water, you obtain typically in some proportions, of course, you obtain microemulsions. You can obtain microemulsions. Okay. This is the example that I have in mind because in France we have a practical around this example, and they prepare the microemulsions, they try to characterize it and so on. There are others, of course. I think I have another example later.
The characterization.
Yeah.
How do you characterize this microemulsion, for instance, in your laboratory?
I have never characterized any in my laboratory in the microemulsion during the practical. So basically, they make observations like these ones. I'm going to describe this a little bit. They make observations, macroscopic observations, and they try to see if the microemulsion is. They also put a laser. They use a laser pointer just to see if there is there is light scattering within the microemulsion. So they do this. They make a little bit of conductivity measurements also, just to see if the continuous phase is oil or water, because the water is salted in this case. With salted water, you have high conductivity, and oil has almost no conductivity. And it's a way to see when you measure the conductivity, the ionic conductivity of the solution of the microemulsion, to see what is the curvature of the microemulsion, if the continuous phase is water or if it is oil. This is typically what. And they spend most of the practical to prepare the samples because it's a phase diagram. So once again, it's a lot of work. Okay. So these microemulsions are also called Windsor systems. It's I think it's an English researcher which he has worked a lot on this system, and he has given his name to this kind of system, Windsor systems. So as I told you, water, oil, surfactant, co-surfactant in general, and when you change the co-surfactant concentration, of course, like what we discussed before, you change the spontaneous curvature by adding the co-surfactant. And when you change the spontaneous curvature, you go from direct microemissions, spherical, to lamella, when C0 is equal to 0, to inverse microemulsions. Okay, and you obtain this kind of tube. I don't know what time do I have to finish before Before the HAL. Okay, just to see if I go into details or not. Maybe I think I won't go into details. Okay. And we obtain this kind typical type of phase, ternary phase diagram with microemission. It's a complicated system because you have water, oil, surfactant, co-surfactant. It's a quaternary system. So if you want to plot, to represent the phase diagram of a quaternary system, you need a triangle is not enough. You need another axis. You need to do something in 3D, in 3 dimensions. So what we do, in general, we fix one of the parameters, one of the concentration, for example, and we change the other, and then we can go back to a ternary diagram like this one. Okay. So I think it's not useful to go into details. I just want maybe to give you an example of measurements that has been done in a publication around microemulsions. They have prepared, so this is, I think it's SDS in this case, pentanol, water and dodecan. It's not exactly the same that we use in tutorials because there is no salt into the water here. Well, so this is part of the phase diagram of a microemulsion. Here you have the oil, co-surfactant, and you see that the water over surfactant ratio has been fixed. It's what I told you before. Is to try to decrease the number of free parameters that you have, and to not to be to have a quaternary representation and to go to a ternary representation. And when you do this here, when you go you move along this axis, when you add pentanol, you can go from direct micelles to lamellar. You go through a lamellar phase, okay? Because you change the spontaneous curvature. And when you go in this lamellar phase, if you see that you have small spots here, small spots. If you prepare a lamellar phase here, and then if you add dodecan oil to this lamellar phase, so when you move from this spot to these ones, that means that you add dodecan, typically. What you do, so the dodecan will be entrapped in the hydrophobic part of the lamellar phase, of course. When you add oil to the system, you swell your lamellar phase, because you add more and more oil. The quantity of water is fixed, so you add more and more oil within the hydrophobic part of the surfactant. You swell it. That means that you increase what I called the smectic distance. I don't remember, it's yesterday or the day before. The smectic distance, it's this distance of repetition that you have in the lamellar phase. So if you swell the lamellar phase, you increase the smectic distance. And people who have made these experiments, they have measured this smectic distance by X-rays. It's very easy to measure it because it's a repetition distance. So you measure it, you have a peak when you measure it, this kind of peak. And the diffraction peak here, the position of the diffraction peak here gives you the smectic distance, of course, the repetition distance. It's typically the inverse of the wave vector, okay? When you add dodecan into the system, you see that the peak is moving towards smaller and smaller wave vectors. That means that the smectic pitch or the smectic distance is increasing because it's inverse. Okay, so you see the swelling of the lamellar phase by oil, and they also see something which a little bit more tiny. I mean to explain and to see. They see an enlargement also of this peak, and this is related to fluctuations because when you swell your lamellar phase, you increase the smectic pitch, and I explained you that the bilayers are more sensitive to fluctuations, and you can see this by even calculate this by the enlargement of the X-ray data. So it's a very nice work which has been done to fully characterize these phases. Okay. Microemulsion, macroemulsion, detergency, very quick because it's very easy, very qualitative. We can use either microemulsion, swelling of micelles or emulsions to wash things, clothes, and when you wash, you also dishes. Thank you, the dishes. And this is what is called detergency. How does it work? Simply, you swell existing micelles, so you have to be above the CMC, of course. You swell existing micelles with oil, fats, and so on. And then you encapsulate, you encapsulate your oil, you trap your oil inside the micelles. So the oil which is not soluble become soluble via the encapsulation into the micelles. So this is on this picture. It is the example of microemulsion, if you want. It's a microemulsion, but this can also be done via an emulsification process, of course. And I think I have just a funny picture where you see the oil soil here and the attack of detergent, of surfactants on the oil, and then it's removed from the surface where it is, and then taken into water, and then you have washed. It's dispersed. Okay. Last, maybe not last, but we see. I don't remember. Another example of the use of surfactant. This is close to what I do in my lab. We are working on carbon nanotubes, so you see it's not so far. Surfactant, carbon nanotubes, so on. And we use surfactant to disperse carbon nanotubes. But this is what I will explain here is very general. I mean, when you want to disperse nanoparticles in general into water or into a solvent, it's very common, very current to use surfactants or amphiphilic polymers. It can be also, or rather surfactant or amphiphilic polymers to disperse nanoparticles. So in the example of carbon nanotubes, I know a little bit more than other nanoparticles. I think you know a lot of things now about carbon nanotubes. You know that in particular they are very interesting because of their exceptional properties. We want to use them, we want to process them to make materials with them. But the problem is that they are insoluble, totally insoluble in any solvent. Or if you at very, very, very few quantities. So if you want to process carbon nanotubes, and if you cannot solubilize them into a solvent, it's very complicated because the raw powder of nanotubes looks like this. It's a suit in which they are completely entangled, disordered. There are strong van der Waals interaction in between them, which entangles them. So it's very complicated. You cannot use their very nice properties like this. So you have to process them. And a way to process them is to put them into a liquid, okay, any solvent, in a solvent, but because they are insoluble, you cannot do this without the help of something. And this thing is the surfactant, the use of surfactants. You have two ways to solubilize carbon nanotubes. Rather, you can functionalize them, you can attach to the surface covalent bondings, covalent species, but it's not so easy, and there are some drawbacks of this method. And another method is to use non-covalent functionalization of nanotubes using amphiphilic molecules like surfactants, for example. So in this case, it's easier. What do? You put your nanotubes into water, and you add surfactant into this solution, and you add surfactant above the CMC. Okay, you are above the CMC, and then the surfactant will adsorb onto the surface of carbon nanotubes. Because carbon nanotubes are hydrophobic, the hydrophobic tail of the surfactant will stack onto the nanotube, will adsorb onto the nanotube, and the hydrophilic head, here in violin, the hydrophilic head will be turned towards the solvent, water in this case. Okay. If you don't use water, if you use another, an organic solvent, you have to change the type of surfactant or of amphiphilic polymers that you use, of course. You have to fit it to the solvent that you use. And this works you have free micelles in your solution, okay, of surfactant, isolated surfactant, of course, like it's also the case when you don't have carbon nanotubes, and you have nanotubes covered by surfactants, kind of micelles of nanotube. It's a kind of emulsion, if you want, where instead of having oil, you have nanotubes inside the micelles of surfactants. Okay. So it's a very current method, and at the beginning, when people were using this method, they were thinking that in order to well disperse the nanotube in the water, the best thing is to put a lot of surfactant. They said if you put a lot of surfactant, you are sure to disperse very well the nanotubes. It was not the case. It was not the case at all. In fact, there is an optimum concentration of SDS, of surfactant, sorry, because it's very often SDS that we use, of surfactant to put in the solution. Why? For the following reasons. If you don't put enough surfactant, of course, you don't have enough surfactant to absorb on the surface of nanotubes. It's clear, it's easy to understand. So you have to be typically above the CMC. It's clear. But, if you don't put enough surfactant, you will keep very big aggregates of nanotubes which are not dispersed. And this is what we see here. It's an optical microscopic image, okay? There is an optimum situation where the surface of nanotube is covered by surfactant, you have free micelle around, and then you have perfect, very good dispersion. Everything is well dispersed. But if you go on adding surfactant in the solution, so maybe it will be better if I put more surfactant. In fact, it's not better, because the surface is saturated by surfactant, and then all what you add will contribute to form free micelles. And there is a particular effect that we call depletion effect. When you have too much free micelles in the solution, these free micelles are applying an osmotic pressure to the nanotubes, and there is a zone in between that we call excluded volume zone, in which if two nanotubes are too close at a moment, if they are too close one to another, there is no more place to have. There is not enough space in between to put free micelles, and then there are a lot of free micelles all around that pushes them, and then they stay aggregated. It's not possible to disperse them. And you observe aggregation here, depletion aggregation, a kind of texture, a specific texture, and inside you have small aggregates, a few dense, not very dense aggregates of nanotube like this one. And it's not very well dispersed in this situation, where it is very well dispersed in this one. Okay? So you have to be careful and to control very well the quantity of surfactants that you add. Okay, I have almost finished my last two transposons. Maybe you know that we can also use surfactants to template matter and to make new materials. I have chosen two examples. The first example is this one, extracted from this research team. They use CTAB micelles. It's a cationic surfactants. And they swell these micelles with a phenolic compounds. In fact, this phenolic compound is typically the type of pollutants that you can find in waters, for example, in dirty waters. Okay, and this phenolic compound is has the property to go inside the micelle, a little bit like a co-surfactant, if you want. It's a little bit amphiphilic, so like a co-surfactant, it goes inside the micelles. Here, this is the small black. You see the phenolic compound. It's here within the micelles. And when you add a precursor of silica inside the solution of micelle, which contains, so you have water all around micelles swollen with this phenolic compound, and you have water all around. If you put a precursor of silica inside, which is called TMOS, inside water, in some condition, by changing the pH, you can solidify the silica around the micelles. In this case, it's cylindrical micelles, but it could be spherical micelles. And then, by solidifying this silica, you will entrap the pollutant inside a solid matrix, and it's a way, a common way, an easy way to dispose of this, to control the entrapment of this pollutant, and to have easy disposal of it after that. So this is an example where you use the micelle to entrap a compound and then to solidify around a solid. Another very nice example, it's this one. This is, of course, a lamellar phase of surfactant, and people are able to put DNA rods, okay, inside this lamellar phase of surfactant. I think it's a cationic surfactant. The DNA rods are going in the water, so they are in the in between, of course, the hydrophilic heads, and they, in some conditions, playing with the quantity, the smectic distance, the smectic pitch of the lamellar phase, and playing with the concentration of DNA rods, it's possible to self-organize the DNA rods onto a rectangular lattice. And of course, the Saffinia, which is the precursor of this work, has done a lot of characterization, and it's a way to organize DNA, and then after that to study DNA, to study the properties of DNA, for example, to measure the curvature, the elastic constants of DNA, because via X-ray it's possible to do that once you have organized it within the lamellar phase. So you see that in this case you use the self-organization of surfactant to induce the organization of another species, and then to study it more easily than if you have disordered rods of DNA. Moreover, it can be, for some extent, interesting to order rods of DNA for some applications. So it's a typical also example of using this self-organization of surfactants. Okay, I think it's my last slide. I was clear. I tried to be clear most of the time. If you have questions now concerning this, yeah, you take the microphone.
I have 2 or 3 questions. Please, could you put the dispersion slide of nanotube? Yeah. This one maybe? Yes. I don't know. I want that if you could repeat what is the influence of the CMC in a good dispersion of carbon nanotube, and what is the influence of the CMC if I change the carbon nanotube for another nanoparticle, another kind of nanoparticle?
Well, in fact, it's a question of balance between the quantity of surfactant that you have and the specific, the quantity of area that you develop with your nanoparticle. I don't know if it's clear. The smallest the nanoparticles, the more interface you will have to cover with surfactant. So when you make small calculation, how many use of surfactant do I need to cover such a quantity of surface? For example, if I have, you can calculate all of this. You take the mean value, the mean diameter of your nanoparticle, you calculate the surface for one nanoparticle, then you know that you have this concentration of nanoparticles, and you can calculate the total surface area that you have of nanoparticle. Then you can know the quantity area of your polar heads, for example. It's possible to know that for a given surfactant. And you know quantity of molecules of surfactant that you need to cover this. But you see that it's an equilibrium between isolated surfactant, at least. You also have a surfactant within the solution which remain free or as micelles. So you need to be above, at least you need to be above this value that you calculate, the number of molecules that you have, that you need to cover your surface, the nanoparticle surface. And generally, when you calculate this, whatever the size of the particle, whatever the quantity, you always have to be above the CMC. That is clear. Okay, if you are below the CMC, you don't have enough surfactant to cover your nanoparticles. So you have to be above the CMC. You have a certain range, a possible range, but you have seen that you don't have to be at too high of surfactant because of this depletion effect. It's clear? Yeah.
And in terms of to control the shape or the size of this nanoparticle, you can be used surfactant too, no?
Yeah. If you want to synthesize it.
Yes, but I need to control the shape and the growing of this nanoparticle. For example, I need to control, in my case, an aluminum shapes, and usually we can use some kind of surfactant. But it's a compromise between the CMC and this area surface, but it's too difficult to control the shape and the growing. It's difficult. It's very difficult to control the shape of this nanoparticle and the growing of this nanoparticle is in a solution in a bulk medium.
Yeah. So if I understand correctly, your question is it possible to control the shape of the particle by playing with the shape of the micelles, for example? You mean, for example, if you use a cylindrical micelle, will you obtain rods? Well, in the best world, it's possible. I know I'm not a specialist of nanoparticle synthesis, but I know that some people are working on that, and in some extent they succeeded in doing that, playing with. But I know that it's also very tiny. It's very tiny because you have the crystal growth in competition with the shape of the way the crystal grows can sometimes induce changes in the phase that you have. I mean, it's not always easy to control totally the synthesis of the nanoparticle with the shape of the micellar structure because due to the condition of synthesis, sometimes you change your phase. There are some examples when, for example, you are in a cylindrical phase, you try to make your synthesis into a cylindrical phase, but because of the synthesis, the phase, you lose your cylindrical phase, surfactant phase. So I know that it's not so easy. It's not so easy, but.
Sorry. You have to remove this surfactant after you disperse the nanotube. What method do you use?
It depends on what you want to do after that. In our case, we are taking these dispersions and then we are making fibers of carbon nanotubes with this dispersion. So in this case, I don't want to. We can discuss after if you want details, but in this case, we replace the surfactant by another polymer at the surface of nanotube, which plays the role of a glue between the nanotubes. But it depends on what you want to do. Very often, it's clear that people, after that, if they use a dispersion to make films, for example, so you can take your dispersion, dry the dispersion, then you have a film. And the surfactant stays in this case, but it can be a problem. For example, if you want to have a good conductivity between the nanotube, if you have a layer of surfactant in between, it's a problem because the surfactant is not always conducting. So it's better to remove it. But you can use thermal treatments or chemical treatments or rinsing at least to remove it. So maybe I don't know if in Merida or in Cumana, do you have questions?
Yes, in Merida.
Okay.
I have two questions about the surfactant or AOT. You mentioned that this surfactant made in micelle. It happened in all conformers or to AOT?
Did you understand the question? No, I'm sorry. Camilo, can you help me with Spanish, maybe? Yeah.
Ok,
¿Puedes hacer la pregunta en español, por favor?
Ok. Ella mencionó que el AOT tiende a formar micelas inversas. Esto pasa con todos los conformeros del AOT.
AOT. Yes. This is the only thing I understood. AOT.
¿Puedes repetir, por favor, más lentamente?
Ok. Forma micelas inversas según lo que ella dijo. ¿Sí?
L'AOT fait de face inverse? Oui, sí. Ajá. Please, go ahead.
Esto pasa con todos los conformeros del AOT.
Que si tú se pasa de l'AOT de la même façon. Ils font de micelle inverse.
Ah, yes. Okay. Sorry. Yes, with AOT you generally only obtain inverse micelles. Okay, inverse curvatures. So it's possible to have with AOT cylindrical, spherical, and I think it's more difficult to go to lamella. I don't have, I must confess, I don't have in mind the phase diagram, the complete phase diagram of AOT, but it's not possible with AOT to make direct micelles. The only way would be to add another surfactant, okay, to force the curvature to change. You see? Can you hear me?
Yes, but
okay.
Yes. It's more difficult for this surfactant change the curvature?
To change the curvature? No, I don't think. The fact is that it is a very, very negative, strongly negative C0 spontaneous curvature. You see? So if you want to change it, you have to play very strongly with physical and chemical parameters. For example, you have to add to the solution a co-surfactant and to add big quantities of co-surfactant if you want to change this, okay, of course, because it's a very strongly inversed surfactant by itself. Okay?
Okay, thank you.
Other questions? This was in Merida, I think, but in Cumana or UCB? No?
En Cumaná no tenemos preguntas.
No more questions. Okay, thank you very much. Thank you. Bye. Bye.
Bye.